Thanks for the introduction. Thanks for the organizers for the invitation. It's nice to be at least virtually in Frankfurt. And today I will report on joint work with José Burgos, Walter Gubler, and Philipp Jell. And it's mainly about a recent preprint, which has the same title as this talk. And this builds on a previous paper, which appeared this year in Mathematische Zeitschrift. I will say a little bit about pluripotential theory for tropical toric varieties. I will in particular introduce them. And then there are two kinds of applications, one to Monge-Ampère equations on toric varieties, and one to Monge-Ampère equation on abelian varieties. So let's start with tropical toric varieties. So we have the usual setup of toric geometry. We have a free abelian group of rank n, and we look at the dual lattice. Then we have a rational polyhedral fan in the associated vector space, and we denote the support like this. And for simplicity, we will need this for some of the statements anyway. We will assume that our fan is smooth. Then there is an associated split torus with character lattice M. It's a spectrum of f of m, where f is your favorite field. And the fan sigma determines non-singular toric variety, which we will always denote by x sigma with the dense torus T. So these are the algebraic varieties, the algebraic toric varieties, which you have seen. So now let's talk about the tropical analog. So for every cone sigma, we have the generated real subvector space in NR, and we look at the quotient space. And the tropical toric variety, or sometimes it's called the partial compactification associated with this fan. Sometimes it's also called a manifold with corners. This is, first of all, this disjoint union of finite dimensional vector spaces. And observe, of course, they are related. So if tau is a phase of sigma, then there's a natural projection map from n of tau to n of sigma. And the idea is now that you consider n of tau as a boundary component of, n of sigma as a boundary component of n of tau. So instead of doing this formally, let me just draw you a picture. So let's look at the tropical projective line. So here we work in the plane. We look at this cone decomposition here, which as an associated toric variety, it just gives us just a projective plane. And then the partial compactification looks like this, where you should think of that this triangle here lies at infinity. Yeah, so inside of here you have the real plane, and then at infinity you compactify like this. Yeah, so locally, because we have assumed that our fan is smooth, locally our space looks like this. So you have some real space r to the n, and then at some components you also allow minus infinity, or you can also do plus infinity. And then you do the topology here such that x becomes a homeomorphism. That's roughly the idea. And this way, n sigma becomes a Hausdorff locally compact space, which has a countable basis. And if you fix a point, and if you fix some direction in the fan, then you can form the point P where you go to infinity in this direction. So this is this limit here. And this means, for example, maybe I draw a picture here. So if you choose your V like this, and you go to infinity here, then you end up precisely here. If you choose your point in here, then you end up in here. If you have your point here and you go to infinity, you end up here. But of course, if you go in the diagonal direction here, yeah, then you will end up here. Yeah, and this holds for any direction you choose in this cone. You always end up in this boundary component. Yeah, so you can go to the boundary, you have a compactification, in all directions which are in the support of your fan. Okay, so these are the tropical toric varieties, and we have discussed a little bit the boundary behavior. So why do we consider them? I mean, they are related to tropicalization. So now let's look at the complex picture. So you have the tropical variety and you have the torus and the toric variety. And now you can look at the associated complex manifolds, which you get by analytification. So here your field is the complex numbers. Then you have the classical tropicalization map. Yeah, so you the complex points of your manifold are given like this, and the map minus log absolute value defines you the tropicalization map. And this map has a natural extension to a proper surjective map. Yeah, so you can go from the complex toric variety to the tropical toric variety in a canonical way, and the compactification is done in such a way that this fits. And of course, for toric varieties, you always have natural action. So inside of C star, you have a maximal torus, that's just a unit disk, or unit circle, I should say. And then you get a maximal real compact torus S infinity, which is n tensor S1. It can also be described as a pre-image of 0 under the tropicalization map inside of this torus. And of course, the torus acts on the toric variety. So S infinity also acts, and then you can check that the map trop infinity just describes the orbit space for this action. Yeah. So the tropical toric variety is the quotient of the toric variety by the action of S infinity. And now something similar holds in the non-Archimedean world. So here we fix a non-Archimedean ground field. Yeah, so we want a field together with an absolute value which satisfies the ultrametric triangle inequality. We want the field to be complete and non-trivially valued. And then we get an associated valuation, and we have also a value group for these data. And for example, you can choose here QP or many other fields. And then you can talk about the non-Archimedean analytification. I will not say very much about this in the sense of Berkovich. Let me just give you one example. So at least for the underlying set, the analytification is just given by bounded, sorry, I think I can delete the bounded here. That's not necessary. So you just take multiplicative semi-norms on a K of M, yeah, on the group ring here, with the property that if you restrict to K, then you get the given valuation on the ground field. Yeah, so the bounded should be deleted because this doesn't make sense. And using this description, you also get a tropicalization map. Yeah, where now a semi-norm is mapped to the map. So it's again given by minus log of the semi-norm. And again, this map extends. Here, this was observed by Kashiwara and Payne, again to a continuous, proper, and surjective map. And here you also have actions. So inside of the analytification of the torus, that's an analytic group. You have a maximal affinoid torus. Again, it's the pre-image of 0 under this tropicalization map. And of course, the maximal affinoid torus acts. And then again, the tropicalization describes the orbit space for this action. So you have to be a little bit careful here. These are analytic groups, but the underlying sets do not have a group structure. So when you talk about orbits and so on, you have to do this in the right way. But yeah, Berkovich has taught us how to do this. And if you do this properly, then again, this here is the orbit space. Okay, so now we have introduced the players. So let me talk a little bit about the motivation for this talk. So now we look at some open subset in the tropical toric variety. And then we look at the pre-images under tropicalization. And so now you have a diagram which links, in a sense, the non-Archimedean space here and the complex manifold over here through this tropical object here downstairs. And our aim is now to develop a pluripotential theory here for this tropical toric varieties, which links the pluripotential theory here and the pluripotential theory here. And of course, the pluripotential here should be linked to invariant objects here and here. So invariant for the actions of these compact tori. Yeah, and if I talk about pluripotential theory here, what does this mean? So there should be a theory of plurisubharmonic functions, where in the following I will just shorten this by PSH functions. There should be products for positive 1-1 currents, so in particular a theory of currents. Observe that in general you cannot multiply currents, but positive 1-1 currents can be multiplied, at least for complex manifolds, where this was introduced by Bedford-Taylor. And then we also want to introduce Monge-Ampère measures, and we want to investigate the Calabi-Yau problem, which can be very roughly stated as which measures arise as Monge-Ampère measures. Okay, so this is the motivation. So let's start with plurisubharmonic functions. So we want to define plurisubharmonic functions, and now on an open subset in n sigma. And in real vector spaces, plurisubharmonicity is related to convexity. And here you will see that we do something similar. So we ask, so first of all, we allow that the function also takes the value minus infinity. And then we ask three conditions. The function should be upper semi-continuous. If we restrict it to an open subset in this finite dimensional real vector space, then we want this function to be convex. So this means if I have 2 points and the segment which connects the 2 points is contained in the set, then I want the restriction to be a convex function as you all know it. And finally, if I have a point P, which is in the interior of n sigma, so in this real vector space, which is somehow the dense orbit, and you have some direction to go to the boundary, and the line from P to the boundary is completely contained in U, then the value at the boundary is less or equal than the value of P. Okay, so that's the definition, and now you can start. I mean, of course, it's made so that you mimic the theory which is well-known and well-developed on complex manifolds. So now you start to check properties. So first of all, you can check this is a local property. Then if you have a decreasing family of PSH functions, you can show that the limit exists pointwise and that the resulting function is again a PSH function. You can show that if your function is PSH and if you fix a cone, then you have the associated real vector space n of sigma, which might of course be now in the boundary, and you get an open set. And if this open set is connected, then the restriction of this function is either a finite function. So by finite, I mean that it does not take the value minus infinity. So it's finite and convex, or it's a constant equal to minus infinity. And finally, if the fan sigma is complete, then any PSH function phi on n sigma is already constant. Now, when you work with PSH functions, then one important characterization is in terms of the positivity on currents. And so we try to do something similar here. And in order to do this, we have to introduce form and currents. So they popped already up in the talk of Walter Gubler 2 weeks ago. So let me briefly recall. So we have Lagerberg forms and currents. These are somehow the good differential forms for tropical geometry. So you want to define forms on NR. So on open subsets on this finite dimensional real vector space, you take the classical sheaf of differential forms in degree P, and you tensor it over the field C infinity functions with itself, maybe now in a different degree. And what you get, these are the PQ forms of Lagerberg. These forms come with differentials d prime and d double prime, and there's a canonical integral for forms of maximal degree over the complex numbers, maximal degree of the forms. Yeah. And of course, this is made to mimic the theory of complex PQ forms. So if you fix the z basis of M, then you get coordinates on your vector space, and then you can write your Lagerberg forms in these coordinates. You have a presentation like this. You have smooth functions here, and there's a formula for the d prime, which looks like the corresponding formulas in complex analysis. And but of course, now we do not just want to work with NR, but we want to work with this compactification. Yeah, so now we observe, first of all, n sigma is a tropical manifold in the sense of introduced by Jell, Shaw, and Smacker. And they have also investigated the question how to extend these forms here. And I will just give you the result. So they say that the good extension is that I take a section of, so a PQ form on an open subset in n sigma is in fact given by a smooth Lagerberg form on this open subset in this finite dimensional real vector space. And then I have to put some condition at the boundary. And the condition at the boundary is that my form becomes constant when I go to the boundary. Yeah, so recall, whenever you have a boundary component, you have a projection map to the boundary. And you want that your differential form comes by pullback from the boundary along this projection map. Not everywhere, but at least close to the boundary. This has a number of advantages. Let me just mention one. You still have this integral here. Yeah, so of course, when you compactify, the definition that something has compact support becomes weaker, yeah, because n sigma might even be compact itself. So then the support is always compact. But if you have something of top degree, then the condition that it becomes constant towards the boundary makes always that your function becomes 0 at the boundary. Yeah, because if it would come by pullback from the boundary, it would come from a form in smaller maximal degree. And so if your form has maximal degree, this won't happen. Yeah, so in top degree, constant towards the boundary means actually that it vanishes at the boundary. Okay, so these are somehow the good forms which we should use to work here, introduced by Jell, Shaw, and Smacker. And then there are corresponding sheaves of Lagerberg currents, which you define by the same procedure as in complex analysis. You have to be a little bit careful to take also care of this condition that it's constant at the boundary, but you can do this. So you can define these currents here, you can define these currents here, and you can also talk about positivity. Yeah, so positivity, that's something, because NR extends, that you can always check in NR. And there, these are somehow forms, and you can introduce positivity a little bit along the same lines as you do this for complex manifolds. So I won't give details of this here, but instead tell you how we can use this now. So I want to give more properties of PSH functions. I will need one more definition. So we call this function strongly upper semi-continuous if for every subset E, which has the property that it has Lebesgue measure 0 in the generic fiber. And for every point A, phi of A is actually equal to this lim sub. Yeah, so upper semi-continuous means that phi of A is greater or equal to this. And if it's at every point even equal, then we call it strongly upper semi-continuous. So then here we have more properties of PSH functions. So the first, which is something which is not true in the complex world. So there you really have upper semi-continuous PSH functions, which are not continuous, but here in this tropical setup, a PSH function is always continuous. Then here's a current characterization. The function phi is PSH if and only if it is strongly upper semi-continuous. The restriction to the open subset in NR is locally integrable. Yeah, and the Lagerberg current is positive. So you need this condition here in order to define this Lagerberg current. And then you take the derivative in the sense of currents. And if this is positive, then this is also equivalent to the PSH condition here. And then finally, we have a local regularization. So the function phi is PSH if and only if phi is locally a decreasing limit of smooth PSH functions. And this property is always important to extend constructions from smooth to all PSH functions. And if you want to prove this, I will not give details of the proof, but the important result behind this proof is the following. And this is from the paper in Mathematische Zeitschrift, which I mentioned, where we compare positivity in complex and tropical geometry. So start with an open subset in this tropical manifold. Then there's a canonical pullback map here. And observe, of course, that the map trop infinity is a map from a complex manifold, where you have complex PQ forms, to the tropical manifold, where you have these real Lagerberg forms. Yeah, nevertheless, you can define a map from here to here, and it will even preserve a compact support because the map trop is proper. And of course, something which comes from U will automatically be invariant under S infinity. But the real forms here will not be mapped to real forms here. Nevertheless, the image you can is invariant under some canonical involution F, which I do not want to discuss here. And this map is made in such a way that if U is contained in NR, yeah, so this map here is an isomorphism if U is a subset of NR. But as soon as U also meets the boundary, yeah, then we have here the condition that our forms become a constant at the boundary. And here we have the condition that this extends to the complex manifold also at the other orbits. And these conditions are in a different nature. And so this is no longer an isomorphism if U meets the boundary. Yeah, then this map induces a dual map on currents like this. And here again, this map, if U meets the boundary, this map will not be an isomorphism. Yeah, but then nevertheless, the following surprising connection holds. Namely, you still have an isomorphism between the S-invariant positive complex currents, which are closed with respect to del and del bar, and the positive Lagerberg currents, which are close to d prime and d double prime. So if you require positivity and that your forms are closed for these canonical differentials, then this map gives an isomorphism. Yeah, and here observe, this statement is really wrong. So there are counterexamples if you don't assume closeness or positivity. Yeah, and if you use this, then you can compare the tropical and the complex picture, and you can prove the theorem I mentioned before. And you can also use this, or what we have done before, to do tropical Bedford-Taylor theory. So if you have locally bounded PSH functions on an open subset, again here in the tropical toric variety, then you can compute d prime, d double prime of these ui. Because these functions are locally bounded, they define currents. You can take the derivatives. And then, as I said to you before, in general, there's no product for currents, but here there is. And it's unique if you require the following properties. So you want that this is determined locally on U. So if you make U smaller, you still get the same product. Then if your functions are smooth, then of course the d prime, d double prime of your function is a smooth form, and you can multiply these smooth forms. And then you want that the formation is continuous with respect to uniform convergence of PSH functions. And now if you remember that our PSH functions are locally monotone limits of smooth PSH functions, you see that these conditions determine the product uniquely. Yeah, and we also talked about Monge-Ampère measures. So observe that if Q is equal to N, and if you omit the function here, then this product here is just a product of positive 1,1 currents. So this is then a positive current in a top degree, and positive currents in top degree are nothing else but Radon measures. Yeah, so this construction gives you in particular a measure over here by this Bedford-Taylor theory. Okay, so now we have a construction of measures, which are these Monge-Ampère measures, and we want to apply this. And in the following, we want to work in the situation where the fan is complete. And in this case, we have seen already that all PSH functions are constant. So we have to work with some kind of a relative PSH notion here with respect to some polarization. So all of this can be done in a more general, setup now. I want to do it just in the toric one because that's what we want to investigate here. So we assume that the fan is complete.
There is a question in the chat, actually.
Yeah, I cannot read it.
Oh, Matthias is asking, are these Monge-Ampère measures supported on NR?
Well, let's talk about this later. When formally, I have not yet said what is the Monge-Ampère measure. I will comment on this later. Okay, so let's fix a strictly concave support function such that each sigma in sigma we have that the function is linear and it even has integral slopes on each cone. Yeah, so for each cone you have this condition here. Then such a function determines a line bundle L. And if the function is strictly concave, then this line bundle will be ample. And it's a toric line bundle. This means that the action of the torus on the toric variety extends to an action on the line bundle. And this line bundle carries a canonical SW invariant continuous reference metric, which is also induced by this support function. I will not give details of the construction here, but there is a canonical choice in the toric setting, but the toric choice is not a smooth metric. Yeah, so it's just a continuous metric, and this is one we want to use for reference. And for this metric, we can look at so usually you would say if you have a metric, you get a Chern form. But here the metric is only continuous, so it's actually a Chern current. And these will be these currents theta W. And we want some tropical analog of this. And this we get as follows. So for each sigma in sigma, there is an open neighborhood omega sigma of n sigma in n sigma, such that the function m sigma minus psi has a continuous extension. Yeah, and then you can find a unique positive current of type 1,1 theta, which is given as the d prime d double prime of h sigma for h sigma. Yeah, so this is the construction of the theta in the tropical setup, and you should just look at this as a kind of tropical analog of these currents here. We will later see that these thetas are also compatible with respect to tropicalization. Okay, and so then here there is a relative notion. These are the so-called theta PSH functions. So we look at an open subset of n sigma, then a strongly upper semi-continuous function phi, again, which the value minus infinity is allowed. This is called theta PSH. If for any connected component W of U, the function is either minus infinity, or the restriction of this function is locally integrable, so that I can talk about the associated Lagerberg current here. And then I want theta plus d prime d double prime phi to be positive. Yeah, so it's a kind of relative positivity notion with respect to theta. And of course, then again, you will have, at least you can expect, non-trivial theta PSH functions, even in the case where n sigma is compact. Okay, and so here is the first theorem which we have now. There are canonical isomorphisms between the following cones. So now on this complex manifold U infinity, this is now an open subset of the complex toric variety. There is the theory of theta infinity PSH functions in the sense of complex geometry. And here you take the S infinity invariant ones. And these correspond to the continuous theta PSH functions on U. And there's also a corresponding notion in the non-Archimedean world. And all of these correspond. And you can also, when you talk about theta PSH functions, you can also talk about metrics. So you can also look at continuous singular PSH metrics on the associated line bundle on the non-Archimedean space or on the corresponding complex manifold. And so here the correspondence is you compose with the tropicalization map. And if you have these PSH functions, you look at the reference metric and you multiply by E minus phi W. And singular here means that the metric might also take the value infinity at certain places. Okay, so here we have a nice link between the PSH functions in these different setups. And if U is the whole space, then you can even add one other characterization, namely then it's also equivalent to the continuous semi-positive metrics here. So here in the non-Archimedean world, the PSH is a kind of analytic definition using forms, whereas the semi-positivity in the sense of Zhang is a kind of algebraic notion. So here you say something is semi-positive if it can be approximated by semi-positive model metrics, and the model metric is semi-positive if so these are induced by by line bundles on models, and if the special fiber of the line bundle or if the restriction of the line bundle to the special fiber is NEF, then you call it semi-positive. Yeah, and now we want to compare. So in complex geometry, we will use this operator DDC. Then our polarizations theta infinity and theta nu are compatible. And now we look at the associated Monge-Ampère measures. So now this here is a positive NN form. So you can take, it's not a positive NN form, it's a positive NN, it's a positive 1-1 current. So you can take these products by Bedford-Taylor theory. You can do the same in the tropical world, and you can do the same in the non-Archimedean world. And in the non-Archimedean world, I think these Monge-Ampère measures were first introduced by Antoine Chamberlois, even so this was for semi-positive metrics. Yeah, okay, and so now let me come back to Matthias' question. So is this supported in NR? That's a good question. I would think so, but I'm not quite sure. No, I don't see right now where they should be supported in NR. I don't see a restriction. Anyway, no, I don't know. Maybe we can discuss afterwards. So these are the three different Monge-Ampère measures. Yeah, here is the complex one, here is the tropical one, and here is the non-Archimedean one. And all of them are related by tropicalization. Now, the Calabi-Yau problem or the Monge-Ampère equation always asks whether a given measure can be realized as a Monge-Ampère measure. So let's fix some measures now. So let's fix a positive Radon measure. So this is a continuous functional which is a positive on the compactly supported continuous functions on U. So if you have such a measure, then there is a unique S infinity invariant positive Radon measure on the associated complex manifold, which has this measure as an image measure. Yeah, this follows, for example, from the theorem before, but I mean, this is not so difficult. In the non-Archimedean setup, the tropicalization map has a canonical section. Yeah, so here on the real vector space, you map somehow elements to corresponding Gauss norms on the torus, and this extends again to the compactifications here and here. And the image of this map is called the canonical skeleton of the toric variety. And now, given the tropical measure, you get an associated measure as the image measure under this map. And this gives you a Radon measure on the non-Archimedean toric variety, which is supported in the skeleton. Okay, so now we have measures everywhere, and we can start to look for Monge-Ampère equations. And of course, now all the notions have been related. So now let's look at a toric Monge-Ampère equation. So we look at a theta PSH function on U. Then we compose with a tropicalization map, and we get theta W PSH functions on UW. And you also get PSH metrics if you use this function to scale your reference metric. And then you can relate the Monge-Ampère equations. So the following equations are now equivalent. So you look at the first Chern class of the line bundle with this metric. And here, as before, this is now a PSH metric. So this first Churn form is positive, is a positive current, so you can take the wedge product here and you can ask whether this is my mu infinity. And if you compute this, you see that these two terms are the same. So this is, of course, equivalent to this equation here. And this is now equivalent to the tropical Monge-Ampère equation here. And then you can, it's also equivalent to the corresponding Monge-Ampère equation on the non-Archimedean space. Here you can also formulate it like this. Yeah, so all of these Monge-Ampère problems are equivalent. And now, of course, we want to use the fact that on complex manifolds, we know a lot about solutions to these Monge-Ampère equations. So much is known about complex Monge-Ampère equations. So too much so that I will not recall it here. And I think there are probably people, yeah, there are certainly people in the audience who know more about this than me. There's also the non-Archimedean Monge-Ampère problem. This was first studied by Liu on totally degenerate abelian varieties. I will come back to this when we talk later about abelian varieties. There is a unicity result about solutions. So unicity means always unicity up to scaling, which holds quite generally. And this is due to Yuan and Zhang. And a general existence result is due to Buxbaum, Favre, and Johnson in the case where K is discretely valued and the residue characteristic is 0. There are more results, but I do not want to mention them all here. But now, using our correspondence and what we know about a solution of the Monge-Ampère equation in complex geometry, we see, for example, that we can solve Monge-Ampère equation on toric varieties. So now let this here be a positive Radon measure on this toric variety, which is supported in the canonical skeleton. And here I will make the assumption that this measure is really supported in NR. So the measure of the boundary is 0. And then when I want to solve a Monge-Ampère equation, the Monge-Ampère measures always have this degree as their total mass. Yeah, so we have to require that if we want to solve the equation, that this normalization condition holds. And then we see that there exists a unique up to scaling toric continuous singular PSH metric solving the non-Archimedean Monge-Ampère equation. Yeah, so using our correspondence, we get the solution of the non-Archimedean Monge-Ampère equation from the solution of the corresponding complex Monge-Ampère equation. Okay, so this is the first theorem of the paper, so that we can do this in the non-Archimedean setting on toric varieties. And afterwards, we want to apply this now to abelian varieties. But let me say you already that in order to do the application to abelian varieties, we will just use the theory developed here in the case of the trivial toric variety given by the torus. Yeah, so what we have done here for these theta PSH functions on tropical toric varieties, this is for this toric result. But what you get for the torus itself, you can apply to abelian varieties. And that's what I want to discuss next. So I think I have to hurry up a little bit. So tropical toric varieties were used by Mumford, Chalfaltings, and many others, but without using the name when they investigated non-Archimedean uniformization. I think the name appeared first by Mikhalkin and Zharkov in 2008. And I will give the definition of polarized tropical abelian varieties due to Foster, Rabinov, Shukri, and Soto. And so this is just an object quadruple where M and lambda are finitely generated free abelian groups of rank n. Then you have a bilinear pairing, which induces a non-degenerate pairing over R. You want a homomorphism which has a finite co-kernel, and you want that the induced pairing here is symmetric and positive definite. And you call this gamma rational if the pairing here has already values in gamma. And from this, you get a real torus, which you might also call the tropical abelian variety, with integral structure given by n. And this is again a tropical manifold in the sense of Jell, Shaw, and Smucker. So you can talk about forms, Lagerberg forms, and so on. So they arise, for example, in non-Archimedean tropicalization. Or non-Archimedean uniformization. So let's A be a totally degenerate split abelian variety. So these assumptions mean that if you look at the non-Archimedean analytification, you can write it as a quotient of a torus by some lattice. So lattice is inside of the k rational points. And this is the non-Archimedean uniformization. If M is a character lattice of T and N the dual, then you get a natural pairing here. You can look at the torus T dual with character lattice lambda, and then you see that the dual abelian variety can be written as a quotient of this torus by M. So then if you have a polarization of your variety, you get a map of tori, you get a map of the character lattices, and all of these data together define you a tropical abelian variety. So this defines a dimension and degree preserving, essentially surjective functor from polarized, totally degenerate split abelian varieties to these gamma rational polarized tropical abelian varieties. Yeah, so there's also some kind of tropicalization. If you want to do this in the Archimedean situation, so then you look at a polarized complex abelian variety. Then, of course, you have again some uniformization. Yeah, so you have a Riemann form. The imaginary part is z-valued and so on. And but now, when you want to make the same construction as before, you need some kind of Tate uniformization. So you do not want to define an element you want to define by a vector space, but you want to define a complex torus or a complex algebraic torus. Yeah, and in order to do this, you need an extra datum, at least in order to do it in a canonical way. So a decomposition for a polarized complex abelian variety is a direct sum decomposition. So you want to decompose your lattice in such a way that this is isotropic for E, for this z-valued form here. Such decompositions always exist. And if you give yourself such a decomposition, then you can define n like this, and you get a lattice lambda inside of the complex torus here, and you get a complex Tate uniformization. Yeah, and then when you have this Tate uniformization, you can proceed precisely as in the non-Archimedean situation, and you get again a dimension and degree preserving essentially surjective functor. So whenever you have a decomposed polarized abelian variety over C, you get a polarized tropical abelian variety. Yeah, so these, yeah, so, but you need this decomposition in order to make this really canonical. Okay, and this allows again to link the non-Archimedean and the Archimedean world. So now we say that a polarized, totally degenerate split abelian variety A nu, which is defined over K, and a decomposed complex polarized abelian variety here, they correspond to each other if their tropicalizations are isomorphic. Yeah, so there does not have to be a common field of definition or something. You just say they correspond to each other if their tropicalizations are the same. So in particular, if you fix some non-Archimedean polarized abelian variety, you can always choose a corresponding complex one because the functor was essentially surjective. And if you want to go vice versa, of course, here the tropicalization has to be gamma rational. Anyway, we start with non-Archimedean, we get a complex one, and we have a common tropicalization. Then you have the tropicalization maps on the torus, and these are respected by the group action of the lattice. So these maps descend to tropicalizations on the abelian varieties, and this holds if in the Archimedean and in the non-Archimedean situation. Then I will not give formulas here, it's a different construction as before, but our tropical abelian varieties are polarized, so you can use this to construct a positive 1-1 form theta out of the polarization data, and you also get polarizations here in the analytification. And these canonical polarizations are invariant under the lattice, so they descend to forms on the tropical abelian variety or tropical torus, and also on these abelian varieties here. So now we have again polarizations here and here, and we can start to talk about PSH functions. I will not give you all the detailed definitions here, but you get again a correspondence, the S infinity invariant omega infinity PSH functions here, and the PSH functions here, and theta PSH functions here. I think it should be omega here, sorry. They correspond to each other. Yeah, so you have canonical isomorphisms. And when we want to discuss Monge-Ampère equations, then we should fix measures here. So we put the usual normalization condition so that otherwise the Monge-Ampère equation cannot hold. So we start with a positive measure in the tropical situation. Then we get associated invariant measures on the abelian variety. And in the non-Archimedean situation, this is supported again in the skeleton, and the skeleton is again the image of a canonical section of the tropicalization map. Yeah, so now you see here that the skeleton in this situation is now a real torus. And so again, we have made compatible choices of Radon measures. And so we can ask for solutions of the corresponding Monge-Ampère equation. So here is the complex Monge-Ampère equation. Here is the tropical one, and here is the non-Archimedean one. And you look at the corresponding spaces of solutions inside of the Plurisubharmonic functions here with respect to omega now. Okay, and now we can use that it is well known that Monge-Ampère equation on complex abelian varieties has unique invariant solution up to scaling. And if we use this plus the correspondence here, then we see that the tropical and also the non-Archimedean Monge-Ampère equation on the tropical torus or on the non-Archimedean uniformization has a unique, and here in the non-Archimedean situation, even invariant solution up to scaling. And this was shown before by Liu in the situation where mu has a smooth density function. Yeah, so if mu has a smooth density function, then the existence of the smooth non-Archimedean solution was shown by Liu. And he also worked with the skeleton, and he used results about the real Monge-Ampère problem on real tori in order to deal with this case here. So we generalize the result of Liu in two ways. So first of all, we allow more general measures. So here it's only measures with a smooth density. And the result of Liu is only in the setup where the abelian variety is totally degenerate. So here we also generalize to general abelian varieties. Yeah, so we do no longer make this assumption that it's totally degenerate. So now we take any abelian variety over K. We look at an ample line bundle and the associated polarization. Then you have to do a finite separable extension of K so that you can do non-Archimedean uniformization and Renault extension and so on. Then there is an extended tropicalization. First of all, there's an extended uniformization, an extended tropicalization map, which was introduced by Gubler. And you can also define the tropicalization of this abelian variety. Of course, this tropical variety only takes care of the batch reduction part now. Yeah, so this is no longer dimension preserving. So if I have totally degenerate reduction, then this dimension stays the same here. If I have good reduction, then of course the tropicalization will be just of dimension 0. Yeah, so then you have this extended tropicalization map. This map has a canonical section, and the pre-image of the image of this section is again the skeleton, and then by some Galois descent arguments, the skeleton even descends to the skeleton in the non-Archimedean uniformization. So there's always a canonical skeleton, and then we can show that if we have a positive Radon measure on the analytification, which is supported in this canonical skeleton, which has this normalization property, then we find a continuous semi-positive metric, which is unique up to scaling, which solves the corresponding Monge-Ampère equation. Yeah, so here we have the generalization of Liu's result for more general measures and without the assumption that it's totally degenerate. Okay, thank you for your attention.